and I want to show closed captions. Okay, let's talk about the relationship between Boolean expressions and I/O tables because it's easy to understand once you see what everything means. All right, so usually I give you 3 or 4 expressions inside parentheses, but we could start with just 2. How about something like P and Q and not R, or not P and not Q and R? All right, so what we do is we write what is true, i.e., the expression tells us exactly when the output, and we usually call it S, is equal to 1, which means it's a hot wire coming out. It means it'll light up the light bulb that's attached to the circuit. All right, so we have 1, 2, 3 variables. We have P, Q, and R. How many rows will our truth table need, or our I/O table? How many rows if we have 3 inputs, 3 variables, and then we'll have 1 output? All right, so let me show you how to count that. We have 2 choices for P. It can be 1, true, hot, or it can be O, false, cold. Hot means there's electricity running through its wire. Cold means there's no electricity. So we have 2 choices for P. It's 1 or O, times 2 choices for Q. It's 1 or O, times 2 choices for R, because it's 1 or O. So what's 2 times 2 times 2?
8.
Yep. So under P, we write 1, 1, 1, 1. We put the ones first, Jessica. If you use AI, it's going to put the O's first. But we always put the ones first, and then we put 4 O's. We just split the 8 in half, and we give the P 4 ones followed by 4 O's. The Q, well, we split 4 in half. That's 2 ones, 2 O's, 2 ones, 2 O's. Then we split the 2 in half. Of course, half of 2 is 1, and that means we have 1 of each, but we always start with the 1. So we have 1, 1, then 1, 0, 1, 1, 1, 0, just alternate. Okay? And this way we do not miss any input state. Let me explain what an input state is. There are 8 input states. An input state is a description of what's coming in to the circuit. This circuit's going to have a P wire coming in, a Q wire coming in, and an R wire coming in. And then there's some kind of machinery in here. We just call this a black box. And then there's going to be an output wire. Okay? We could ignore what the circuit is for the moment. So an input state is the information about what's coming in. For example, in row 1, P is hot, Q is hot, and R is hot. So the Boolean expression for the input state can be written down for each of these 8 input states. For row 1, we have P and Q and R because we write what's true. P is hot and Q is hot and R is hot. That is a description of this input state where all three of these wires going in are hot wires. They have juice, they have electricity running through them. Okay? Can you tell me what the Boolean expression is for the second row? Either one of you.
The Boolean expression for the second row, meaning Q, or no, okay.
It's going to be
It's
information
P,
about P. Okay. P is hot, good.
and Q,
And Q.
and not R.
That's right, and not R. Notice we're connecting these bits of information with ands because all of this is happening at the same time for this input state. It means P is hot and Q is hot and, well, not R is what's hot, so that means R is cold. We write what's actually true. This is the actual input. A hot wire for P and Q, so there's a 1 on P and a 1 on Q, but the cold wire, R, is there. What about the expression for row 3? Jessica, you want to give it a shot?
P is hot, or sorry, P and Q. Sorry, not Q, not Q,
Good,
not Q,
good, good.
and R.
Perfect. Fantastic. How about row 4? Ibrahimo, can you give me the Boolean
Sure.
expression that
hmm
describes the input of row 4?
Yes, ma'am. P and not Q and not R.
Perfect. Now we're cooking with gas. Let's
Okay.
keep going. Row 5, Jessica.
Um, not P
Good.
and Q and
Yep,
R.
exactly. Ibrahima, row 6.
Not P and Q and not R.
Exactly. Row 7, Jessica.
Not P, not Q and R.
Yep. It's an and between everything because all of this is happening at the same time.
hmm
And finally, the last one.
Not P and not Q and not R.
Great. These are the 8 different possibilities for inputting the wires when we have 3 input wires. Now, the Boolean expression that I gave in example 1 is a description of the input states that will give us a hot output. All the other input states give a cold output because if they gave a hot output, we would have written their expressions with an or between them and the ones we have here. You see, what this says is if this is what's being input, we get a hot output. Or if this is the input state, we get a hot output. That's why we put an or between these expressions that have ands. All this happens at the same time, or all this happens at the same time. If either of those happens as the input, then the output is 1. So, what rows shall we put S equals 1? In what rows? P and Q and not R. What row is that? This is
P.
row.
Uh-huh. Okay.
Because we want to put a S equals 1 in the row where P is hot and Q is hot and R is cold.
Where P is hot and Q is hot and R is cold.
That's
So
what this means.
okay,
What
yeah.
row is that?
Mm, oh, two.
Good. So we'll
hmm
put hot output for that. Or we want to get a hot output if the expression in this parentheses is our input state. So P is cold and Q is cold and R is hot. What row is that, Jessica?
You said not, which one?
The second
Not P and not
expression.
Q, not P and not Q and R is going to be row 7.
That's right. Those are the 2 rows. that give hot output. We write the expressions that tell us when the output is hot. We write what's true. Having true output or hot output means this is true. Every other one of the possible ways of inputting wires yields a cold output. So we put zeros or O's everywhere else. And that's why we love disjunctive normal form. Disjunctive normal form is like this, where we have an or operator, that's the disjunctive part, between the expressions that give us complete descriptions of the input state. Disjunctive normal form allows us to build the I/O table very quickly directly from the Boolean expression. Now, if we want to build the circuit for this Boolean expression, and it is generally easier to look at the Boolean expression, we just need to understand, okay, we're going to have a P wire, a Q wire, and an R wire because the only variables we see are P, Q, and R. So we'll draw a P wire and a Q wire and an R wire. I'm going to write my expression down here where I can see it. You always want to write your expression where you can see it. Okay. Now, we can only have one input wire for each variable. We cannot repeat the P, Q, and R again. Because if we did, then one copy of P might have electricity on it. That might be a 1. And then maybe a different P would be a different input. We don't want that. We want to control what's coming in. And the way we do that is by letting each variable have a single input wire associated with it. Does that make sense?
Mm-hmm.
Mm-hmm.
Now, there's an order of operations, just like with math. When we do arithmetic, it's please excuse my dear Aunt Sally. We work inside parentheses, then we do exponents, then multiplication and division are equally important, and then addition and subtraction come last. Well, here, parentheses happen first, so we're going to work inside parentheses. Notice inside the parentheses we have nots. We also have AND gates, but we won't have any OR gates inside parentheses when it's in disjunctive normal form, and that makes it kind of easy. We can put the P wire and a Q wire and a not R wire into the same AND gate. We don't need two AND gates because an AND gate can accept more than two wires. It can accept many wires, including 3 wires. So we want to put the P wire into this AND gate. So I'll just put the P wire in. We want the Q wire to go into this AND gate because I'm building, if I call this expression 1, this AND gate is for that expression. And then we'll build a different AND gate for expression 2 down here, okay? Now the Q wire, it's kind of too far away, so I'm going to bring from that Q wire with this solder dot. That means I'm drawing from the Q wire and I'm going to put the Q wire through a NOT gate, and that's going to go into the AND. See it? Oh, did I want not Q there? No, I did not. I just wanted plain old Q. My bad. Let me erase the NOT gate. Thank goodness for whiteout. We just
Yeah,
want
that's
plain.
the next question.
Yeah, good. Yeah, Dr. Good makes mistakes sometimes.
Oh yeah.
Did we get a point?
Sure. Email me for a point of extra credit.
Gotta fight
Hey,
for that
take
point.
it. Take it. You earned it.
Okay.
Now, what do we want to do with the R wire? Because we want to put not R into this AND with the P and the Q wires.
We have to make that one go through a knot.
That one's the one that's going to go through a knot. So I'm going to bring up here and I'm going to bend. You can turn a corner without a solder dot. You're just bending the wire. And then that's going to go through a knot. and that's going to go into the AND. Okay, so P and Q and not R are going into this AND gate, and this AND gate puts out something. Think about it. The only time this AND gate is going to output a hot wire, a 1, is if all three of these wires coming in are hot. But for this wire to be hot, R had to be cold because when it goes through the NOT gate, it'll flip it to hot. See what I mean? And that's why P and Q are hot, but R is cold to make this AND gate output a hot wire. Does that make sense?
I do have a
Uh,
question. When do
Please.
you use the solder dot? I mean, I know we're making a connection is when we use it, but what
Like,
exactly?
why don't we need it like when we turn a corner? We
Yeah.
need it when because
Almost.
when you're just taking like a pair of pliers and just spinning the wire, you don't actually have to solder to meld them together to or weld them together. But look,
Mhm.
I'll show you this Q wire for the other expression. We need a not Q. So here's Q, but we're going to take from that Q wire and we're going to run it through a NOT gate here. So we're splitting the Q wire. Part of the Q wire is going up here, and this is just still Q. But the other Q part of the Q, this is Q right here, but once it goes through the NOT gate, then what's coming out here is not Q. Does that answer your question?
Yeah.
Okay. So to build this second AND gate that's going to be for expression 2, I'll put the AND gate here. I'm going to bend this down so it gets into the AND gate. That's our not Q. But what else needs to go into this second AND gate?
Not P.
And do
So,
we have a not P wire yet?
nah, we need to do a solder dot from P.
Yeah, we're going to draw from P. So this is still P. This value that's here is still here. Imagine if there's electricity running right through here and these are touching, then that electricity is also going to run down this wire. These are not touching. We don't want them to touch. So we just don't put a solder dot there. And we'll bend it and we need to put it through a NOT gate. And now this is our NOT Q wire. It's going to go in there. And what else needs to go into the AND gate?
R.
Yeah, because we've got not P coming in. This is not P. We've got not Q, and we also need R. So we'll just bring the R wire up and we'll just bend it. And so the reason we soldered here is because we drew R up to take it to a different gate than this one. So here's the output wire from this AND. And notice this AND gate is going to output a 1 or a true or a hot wire only if all three of these wires coming in have the value 1. But for this to be a 1, this is not Q. That means Q had to be cold so that it would flip in the NOT gate and become hot here. P had to be cold coming down here, and then it flips it and makes it hot. And then R, when it's hot, then this AND gate will output a hot wire. So these are the two S's having the value 1. This is AND gate 1, and this 1 is what's coming out of AND gate number 2. If this is hot or if this is hot, we want the final output, I'll put it over here, S, to be hot. So we run these through an OR gate. Because if either one of these is hot, we want this to output a hot wire. That's why there's an OR in between,
Mhm.
because that's the last thing that happens in disjunctive normal form. The last gate is always the OR. Now, it could have been that there were several parentheses expressions with ORs between them. Well, this OR could accept 3 or 4 wires. It doesn't just have to be 2. It could have been 3 if there was another or something else here. See what I mean? So let me leave you with a do later, and then you can come into office hours later and show me, or you can take a picture of it and send it to me, and I can look at your work
Okay.
Okay.
Do you have any questions before I do that?
Um,
Mm,
before or I know you were explaining the or at the end. Now I
Yeah, that's
understand.
this or
Yeah,
gate. Uh-huh.
because we always put the one in the middle of the disjunctive normal form. That's what we do as the last gate. If it was an and, it would have been
An and gate here.
okay.
Yeah,
And
and
then
and all of the expressions we see in WebAssign aren't disjunctive normal form. But I
hmm
like disjunctive normal form because it lends itself to this nice, easy application. And
hmm
that's why it's called a normal form. Normal forms are forms that are particularly useful, and they're also universal. Any expression that you're given, even if it doesn't have this form, you can convert it to an equivalent expression that does have disjunctive normal form. So if I give you like P and not Q and R, or P and not Q and not R, or not P and Q and not R, then there's going to be one, two, three AND gates. So there'll be three wires going into that big OR gate at the end, okay?
hmm
So construct the IO table, and you should be able to do it directly from this expression because it is in disjunctive normal form, and draw the circuit. But there's another way to play the game. Another way to play the game is if I give you the IO table. So let's say I give you an IO table. And I'm just making one up. There's nothing particularly special about this, but I'm just making it up. I'm not making up this part. Any three variable IO table is going to start like this. The question is, what am I going to put here? Have you thought about how many different ways I might fill in this column?
mm
Like they could all be ones,
mm.
or half of them could be ones and half of them
Oh,
could be
okay.
O's. The
Because
point
it's
is,
because or
so
okay.
the point is, in each of these 8 rows, S is going to either be value O or value 1, right? So we have two choices for the value of S in row 1 times two choices for the value of S in row 2, because this could be 1 row times this could be 1 row times keep on going all the way down to the 8th row. S could be 1 or O. There's 2 times 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 2, which is 2 to the 8th. 256 different ways I could fill in this column. So
Could
there's,
we do a shortcut?
there a shortcut.
Because like if you just go, because I know you said with going based off it's a different, or is it the same example, 2 and 3? Is that the same exact table or no?
No, no,
Okay.
these are,
Separate.
I'm not gonna give you the answer to two. I'm gonna make up a
Gotcha.
different table, and I'm gonna ask you to find the Boolean expression. So what if we have a 1 here and a 1 here and a 1 here? Can you write the Boolean expression?
Yeah.
Because now you understand the input states, right?
Yeah. Which ones are hot?
Uh-huh. And then draw the circuit. But you'll be writing the Boolean expression in disjunctive normal form. Because remember, the ones that are hot, the information is connected with ands. So in the row, we use ands and not maybe. Okay. We use ands across the row. But then when we connect the different rows that give ones, we connect them with an or. Because if this happens, or if this input state is what's being input. So if this is the input state or if this is the input state, we want the circuit to light up and give us a 1. So you're going to do the same process, but in reverse. You're going to find the Boolean expressions for these rows that have s equals 1, and you're going to connect them with ors in between. Does that make sense?
Okay, so like we
Hmm.
were doing on the last one, so it's gonna
Mm.
be not P and not Q and not R for the first one. Oh, I'm sorry. That's crazy. I'm sorry. It's gonna be P. Yeah, it's gonna be P, Q, and R for the first one. P and Q and R.
Yeah, this is yeah, you're right. This is
Hmm.
P and Q and R because
Okay.
they're all true. They're all we write what's true. We write
Hmm.
what's hot.
Hmm.
And then what about this one?
P
P.
and not Q and R.
Good. Or
Uh,
P and not Q and not R.
great. And then you'll take these three expressions, slap them inside parentheses, and connect the parentheses with ors. Because the point is, what it means is if this is what's input, or if this is what's input, or if this third expression is the input state, we want hot output. We want hot output if this happens as input, or this, or this. Does that make sense now? That's why the ors are where they are. And that's why the ands are where they are, because all three of these have to happen at the same time as to make that input state completely described. Good. I think we've learned something.
oh yeah.
Now, do you have any other questions that you want to talk about? Some other concepts that have been nagging you, bugging you?
Let me
It
think.
was just those two for me, I would say.
Yeah, I know that's what I didn't finish on the test.
Okay, then. So I tell you what, did you finish your Tarski worksheets? I tell you what, if you didn't have a chance to finish your Tarski worksheets, go ahead and try to practice those during the semester because I promise you, you're going to see Tarski again on the final. And
Mm,
this, and I posted the solutions.
okay.
Actually, I know on the test, I mean, I know we can't go over the test, but it was I guess contradictions and tautology.
Tautologies? Yeah.
Yes.
Yeah, let's just review what a contradiction is and what a tautology is. Now, contra means opposing. That's Latin.
Yeah.
Tautology is the other one. Tautology is always true. A contradiction is always false. So we use,
False.
yeah, contradiction is always false. A tautology is always true. And if you go back and look at the class notes from section 2.1 and 2.2, when we first started talking about truth tables, there's a big old do later at the bottom of one of the pages of class notes, and you should do it. But let's just look at some examples. Let's let P be any statement. We don't know what it is. We don't know if it's true or false. It's just a statement, okay? A, construct a contradiction using P and any statement operators you wish. Like you can use and, or, not, if then, or if and only if. Those are our statement operators, right? Now
Hmm.
we don't even know whether P is true or false, right? But our job is to use P, and we might use it more than once, but we're going to use P and some statement operators to create a statement that's always false. And remember, we don't even know if P is true or not. But a contradiction will always be false. Okay, so, we need to make something that's always false. So let me give you a hint. What do you know about the truth value of P relative to the truth value of not P? There's a relationship between the truth value of P and the truth value of its negation. Do you know what that relationship is?
Yeah, but I don't know how to put it into words.
I don't think you need any big words.
Because I mean, if P is true, then not P is gonna be false always,
Correct. And if
and
P is
vice versa.
false, then
Then not P will always be true.
that's right. They have opposite truth values.
Mm.
That's the nature of the negation. When we negate a statement, we get a statement that has the opposite truth value. So, what if we just did this? What if we take P, we don't know if it's true or false. I'm going to leave some room for an operator here. I'm not going to write it yet. I'm going to put not P. So far, all I know is these two will have opposite truth values. Do you agree?
Mhm.
One of these is true for sure, and one of these is false, but I don't know which. Do you know which? Nope.
No, not enough information.
But what if we put an and in between there? Is there any way this could be true?
P and not, I mean, it could be P then, wait, is that two P's?
Yeah, I'm
No,
using
it
P
Oh,
can't be.
twice. It's
It can't be.
P anded with not P.
I mean, could it be P then P?
No, no, no. Just look at what I wrote here.
Okay, okay, okay.
P and not P.
So true
It's an
and
ans.
false, impossible.
Or false and true. The point is, one of these is going to be false. Do we care
Hmm.
which one? No,
Nope.
because and doesn't care.
Yeah.
And will only be true if both of
Both
these are
sides.
true. But we know one of these is false, even though we don't know which one. This is a contradiction. It will
Okay.
always be false. And if we and P with a contradiction, doesn't matter whether P is true or not, it's not going to help because the contradiction is always false. So when we and a contradiction with anything, that anything can't help. This contradiction already makes this and statement false. Does that make sense?
What if it was like if it was the other way around? If it was um so if it was C um and P, it would still be the same thing.
It means the same thing because
Okay.
the and operator is, that's a great question. The and operator is what we call a symmetric operator, kind of like the plus sign, 3 plus 2 equals 2 plus 3. The plus sign doesn't care which side of it the 3 is on and which side the 2 is on, does it?
Mm-mm. Nope.
Multiplication is a symmetric operator. 5 times 4 equals 4 times 5. Times is symmetric. But is the subtraction operator, the minus sign, is it symmetric? Is
No.
7 minus 3 going to equal 3 minus 7?
No.
No.
No, the minus sign is not symmetric. The division symbol is not symmetric. 1 divided by 2 is not equal to 2 divided by 1. But addition and
Mm.
multiplication are symmetric. The and operator is symmetric. It doesn't care which side the components are on. Can you think of another operator that we know that's symmetric?
Mm, I'm not sure.
Equals.
Equals is very symmetric. What about any of these? Are any of these symmetric
Oh,
besides and?
the last one.
If and only if is
If and
symmetric.
only if.
Yep. There's another one in here that's symmetric.
It's not the or, that's for
Yes, it
sure.
is. Does or care what side,
It's either
right?
or.
Or is
Wait, why is it?
evaluated if either
Sorry.
one or both are true. It doesn't care what side of it the true one is on.
Hmm.
So the same problem that we started, P is any statement. We don't know anything about it, but it's a statement. We don't know its truth value, but we do know it's a statement, and we know something about not P. Not P always has the opposite truth value. So for example, for B, guess what I'm going to ask you to do? Contradictions, tautologies. What would be a reasonable thing for me to ask you to do now? Construct a tautology using P and any statement operators you like. So we're going to try to make a statement that's always true. Contradictions are always false. Always. Tautologies are always true. But we can milk the fact that we know something about the relationship between P and its negation, not P, to come up with a solution here. The and operator is not going to help us because that creates something that's a statement form that's always false, right?
Mm-hmm.
But what might help us create a statement form that's always true? What do we know about the relationship between P and its negation, not P?
Um, that they are, I forgot the word you use, not opposites
Opposite.
of each other.
Yeah, they're
Okay,
opposite.
opposites.
They have opposite truth values.
Opposite truth values.
So one of these is going to be true and one is false. We don't know which.
Mm-hmm.
Okay. But we know one is true and one is false. But doesn't the or operator give us a true statement if either one is true? It doesn't have to be both.
Oh, okay. This isn't
Oh,
that.
you're right. True.
Must be
See
Yeah.
it?
something
See
bad
it?
here.
Yeah.
I love that.
Okay.
We could also or P with something else and it'll always be true.
T.
Yes, because the T is always true, and
That's
that's
true.
enough to make the or
So true
statement
or true.
true.
Yeah.
Yeah. So if P is false, doesn't matter. The tautology is true. So the
Mm-hmm.
or operated statement will be true because the tautology component is true. Isn't that cool?
That is.
Mm-hmm.
Yeah. That's smooth. That makes sense.
It does.
Mhm.
What about with the imply symbol?
Okay, now you're going to test Dr. Good's now you're going to test
Mhm.
Dr. Good's knowledge base. I'll tell you one thing that's always true. P if and only
Implies.
if P.
Mm.
Okay.
And actually P implies P will also be true, but this one's a little easier to see. Do you let's just recall the biconditional operator, the if and only if operator. It's called the biconditional when we make a statement out of it. Like A if and only if B. Okay? What what it means to say A if and only if B. In other words, what it means to say this is true it means A and B have the same truth value. Either they're both true or they're both false. So if we made the truth table that describes when A, if and only if B is true, let's just put true, true, false, false under A. You could use P's and Q's, doesn't matter. I'm just using A's and B's, but that's the way we set up the table. A, if and only if B is true when A and B have identical truth values. So you help me fill that in. Knowing that rule, what is going to be in row one? Under
Um,
A, if and only if
T.
B. Yeah, because A and B are both true. It's true. What about
Mm,
in row two?
they have the same truth value. Okay.
But not in row two.
Yeah, that's what I'm saying. So
So,
F, yeah.
so it'll fail. What
Fail,
about row three?
fail again.
F
What
and then
about row
F.
four?
True.
Because they have the same
Oh,
truth
two.
value.
Mm-hmm.
Yeah, yeah.
Two contradictions.
A, if and only if B is true exactly when A and B have identical, doesn't have to be true, just identical truth values. And the interesting thing about it is that rule is sort of easy to remember, but also recall the definition of A if and only if B. The definition of A if and only if B, it's that A if and only if B is the same thing or is logically equivalent to A implies B and B turns around and implies A. So here's a do later. Make a truth table with columns for A, B, A if and only if B, A implies B, B implies A, and finally, A implies B and B implies A. And compare the column for A if and only if B with the column for A implies B and B implies A. We'll call this statement one, okay? We'll call this statement two, okay? So one and two. I want you to prove that these are logically equivalent by looking at their columns. Show one is logically equivalent to two by comparing their columns in your truth table. Those columns, what should they look like? I mean, how should they compare to each other? If this logical equivalence really holds, what should their columns look like relative to one another? That was a question on our test. I gave you two statement forms and I asked you to determine if one and two were logically equivalent and you needed to make a truth table and you needed to build up and make a column for one and a column for two. And the logical equivalence holds if their columns are identical. That's what logical equivalence means. It means that those two statement forms always give the same truth value no matter what choices for inputs A and B you feed into them. That's what it means. See, we've got three different ways we use truth tables. One of the ways is for arguments, okay? For testing argument validity. I think everyone knows that one. You remember that one because we did it more recently. But before we played argument validity games, We played logical equivalence games, and we used truth tables to see if two statement forms are logically equivalent. If their columns are identical, then they're logically equivalent. If their columns differ in even one row, then the two statement forms are not logically equivalent. They don't always give the same output for the same input. The other thing that we used truth tables for was just to learn a rule for a new operator. If you go back and look at the very first pages of notes from chapter 2, the very first application of truth tables was as a shorthand way to understand the rule for our various operators when we were learning our operators. So that's a really good review. Oh, did we lose Jessica? I think we lost Jessica.
I think we might have. Maybe her computer died or something.
Yeah, probably.
Mhm,
Oh, well,
mhm.
my brain's about to die.
I
I'll
believe
see you
it.
tomorrow in class.
Yes, ma'am.
Okay?
I'll see you then. Thank you for
All
your help.
right. Thanks for coming. Thanks for
Yes, ma'am.
playing.
All right. See you.
See you. Bye.
Bye.